Okay, good morning and welcome to this second part of the course. So, some practical information. If you remember from the GitHub repository, you can follow the lectures, and today we will be in the day 2, and the first lecture will be about molecular dynamics simulations. The second part will be about the QMM calculation. So some things that I can tell you from the lesson yesterday is that there were some very interesting questions on the Q&A document. And for instance, there were questions about different GROMACS versions. And also I saw a question regarding the A100 type of GPUs. So these are very interesting questions. And in order to keep track of your interest, I would recommend that you could write a ticket so that my colleagues are aware of the interest that you have regarding the software and the hardware. So it is more convenient if you write the ticket and then we can follow your ideas. So this is one thing. And the second thing that I wanted to tell you is that login notes should be used for only lightweight tasks. So, which means that if you want to do the setup with GROMACS or any other software, NAMD, Amber, then it's okay to use the login notes for this task. But running long jobs creates a issue for the other users because then they will see a slowdown in the codes. So if you want to run long jobs, then you can submit them to the queue, as I mentioned in the talk yesterday. Okay, so let me go to the lecture if there are no further questions regarding the lecture from yesterday. So today we will be talking about classical simulations and also quantum simulations. Let me see. Yeah. So you may be aware that classical MD simulations are quite old. Everything started in 1600s with Isaac Newton, where he was, according to the legend, he was below a tree, and he saw a apple falling down, and it was also during a pandemic. So, and he came up with an idea that the gravitational force was responsible for making the objects falling down. And this idea can be extended to other types of interactions. And in particular here, there is a gravitational force, which is acting on the objects. So, but there are other type of interactions, and this will be what we will be studying today. So you may think why, if this field is quite old, you are still using that. But you may be aware that a few decades ago, we didn't have the software, we didn't have the hardware, and also the algorithms were very primitive. So, and right now, everything is very advanced, algorithm, software, hardware, and that's why instead of computing the equation, solving the equation for a single object like in Apple, we can do now millions of atoms at the same time, right? So according to the Newton's law, we can get the force on the objects by taking the derivative of some function which we call the potential energy function. And this function depends on the positions of the objects, in this case of the atoms. So here is a vector denoting the position for n atoms, and there are three uh, coordinates for each atom because they refer to the spatial coordinates. And in principle, we can get the forces if we know this function here, U, which is the potential energy function. And that's a good point, because just by taking the derivative, we will know how the system will evolve in time. Well, that's in principle, because we don't know exactly how this function looks like. So what the people do in practice is that they try to approximate this function with some empirical potentials, as we will see. Another complication deriving from this equation is that in order to integrate this equation, we need both the positions and the velocities, initial velocities of the particles. And knowing the initial velocities in the real world, it's not possible. So what the people also do is that they approximate the velocities by using some type of distribution, for instance, the Maxwell-Boltzmann distribution. And then one simulates the system based on this initial set of velocities. So that's why a realistic system is quite difficult to simulate. So the U function that I mentioned in the previous slide can be visualized as a landscape. Here it's a landscape with some mountains, and imagine that we are at some point and we want to get to a different point like this in the valley. Yeah, you are at the top and we want to go to the valley, or the other way around, and then we need to follow some trajectory. Yeah, and this illustrates the concept of using the energy. In this case, the energy refers to the gravitational energy, and the conformational space is just the three coordinates of the space. But the situation is very similar in proteins. The only thing that changes is the type of energy function that we use. So the field of molecular dynamics started around the 1950 and most probably earlier than that. But these are the first papers reported on more realistic systems. So for instance, one of the first papers was on hard sphere systems, and then another paper was regarding the motions of atoms in liquid argon, and this one make a breakthrough in the computer simulations, and here Michael Levitt and Ari Waschel simulating the folding of a protein. So based on their discovery, Martin Karplus, Michael Levitt, and Ari Waschel shared the Nobel Prize for the development of multi-scale models for complex chemical systems, and they did not only classical MD simulations, but also combine QMM simulations to treat chemical reactions. So in the past, if you did an experiment in your research, it was most probably enough to get it accepted into the high-profile journal, for instance. But now, when one submits a experimental job, sometimes or frequently, one is asked to back up the results with some theoretical or simulation calculations, or the other way around. Yes. So currently, these three topics, experiment theory and simulations, are very well connected, and one cannot neglect the results from the simulations any longer. So classical simulations can be applied to very different fields, and here I only put a few examples. Like here, this is a adenylate kinase enzyme in water and with some ions in the cell. People also apply that for clays. It's possible. And also in the food industry, there are many applications. For instance, when one tries to study the ice cream or the chocolate mixes, it's also possible to study these matrix systems by using classical MD simulations. In asphalt, you can see there are some nice applications of classical molecular dynamics. So, but now let me go to the classical potential function. And here you can see one possible formula for this potential energy function. We said before that this is a empirical potential. This is not what the nature give you, yeah, but it's just one way to mathematically reproduce or try to reproduce the result that you get from the nature. And there are several terms, and this potential energy function depends on the type of force field that you will use. There are several, and also depends on the package that you use. For instance, GROMACS would have some force field and also charm or NAMD and amber. So, but the concept is essentially the same. There is a bond interaction here, also a interaction related to the angles between the atoms, the torsions, and this is very important, the Coulomb interaction, which is related to the electrostatics or the electrostatic interaction between the atoms, and also this part related to van der Waals interactions, which contains a dispersion part here and also a repulsion part, which comes from the Pauli exclusion principle. So it's better to visualize these interactions with the graphics. Here you can see a protein, and here you can visualize the bond length interaction, which refers to the pairs of atoms, the angle interaction here, the torsion interaction, which involves the four atoms and the bond in between. And this is a periodic function, and that's why one needs to use a cosine like this, a cosine and some periodicity factor here. And also the Lenarions interactions, which decreases with the distance, and it's very repulsive when the atoms approach each other. So this is essential if we want to avoid clashes, especially if we introduce the electrostatic with Coulomb. And we know that the charges will tend to attract until the distance is zero, and this will create a overflow in the calculations. So this is a plot for the different force fields that exist. There are not all the force fields, but these are a few of them. We can see the force field charm 22 OPLS, and there are several versions of charm, including some specific modifications that the people do, like this charm 22 star, where people try to correct the interactions for instance, some dihedrals or some angles, right? So, and imagine that you have a more simple potential energy function. We have seen that in proteins we need the bonds interactions, the angles interactions, dihedrals, and so on. But imagine that we have a more simplistic potential energy function, like a simple the sinus times the cosinus, right? More simplistic. If you plot this function, you will see that there are plenty of maxima and minima. So imagine that you try to see or visualize the realistic potential energy function for a system like a protein. There will be plenty of minima and maxima. And the goal in molecular dynamics is to sample the best we can this potential energy function. So if you start, for instance, from here and we want to go to here, we need to overcome a barrier here, and the same for the others. So if our algorithm is not that good, then we will stay always at this point, and we will never see the rest of the of the surface. So, and that's essential to get a realistic thermodynamical estimates of the properties. So as I said before, there are several types of force fields. For proteins like hydrocarbons, there is a Gromos force field, OPLS and derivatives, Amber force field, and Charm. For clays, there is a force field called clay FF. There are also coarse-grain potentials like the Martini force field. So if your parameters for the compound that you are interested in are not a part of the force field of any of these or any of the existing force fields, then you need to use some QM approach to parameterize that, and in general it takes some time, and it's also an art. So there are many types of water models that we can use, and here I show you only a few of them, and it depends on the number of atoms that you want to consider. Maybe you want to use only 3 sides model, or a 4-side model, which includes a dipole moment here explicitly, or here you include 2 dipole moments in these 5 models. But the cost of the model increases drastically, because here you have 2 more atoms than here, and in general, in a simulation, for instance, in a protein, the water is the most expensive part to solve, because there are many more atoms related to the water than for a protein, for instance. So in proteins, there are 20 amino acid chains, and the parameters for these amino acids are available for the most standard force field like Gromos and Charm and so on. But in general, the people now are interested in some mutations or some known standard amino acids, and parameters may not be available for that particular amino acid, and you need to parameterize that. So if you want to get the structure of a protein, you can go to the protein data bank, and this will provide you the information of the chain or the protein that you can use. Here is an example for the adenylate kinase, and from there you can get an initial crystal structure that you would need to work out, because sometimes there are missing residues, or for instance the hydrogens are not present, and you need to make several reparations to the structure. So the type of simulation that we have seen up to now is just a molecule, right? A protein which can be surrounded by water. But imagine that in a computer we can simulate until 1 million, 5 million atoms, right? For realistic systems, if you take a cup of coffee, for instance, here you will find around 10 to the 23 particles, right? This is the Avogadro number, and you will never, or at least with the current software, you cannot simulate this type of systems. So one uses a trick called periodic boundary conditions, where the first cell is reproduced in the three directions of space. And then when an atom gets out of the cell, then it is reflected in the opposite side of the system. So this creates the type of simulation that can be observed as a more realistic system, because this will look like an infinite system from the simulation point of view. So this is the system that similar to the one that we will work out today, a protein with some water molecules and some ions in the cell. And this will be the main cell of the simulation. So in order to solve the electrostatics, you can use many algorithms, including the cutoff, which is not very realistic for real simulations, but it's possible to use that. Or also you can use some periodic boundary conditions together with a more advanced algorithm like particle mesh Ewald. And here is some initial idea of how the Newton's equations are integrated. We have seen this empirical potential for proteins, for instance, and then once you have this function and all the parameters that are given in the force field you are interested in, let's say charm or gromos, then you take the derivative of that function and then do two integrations, because here there is an acceleration and this is related to the second derivative. So there are many algorithms that allow you to integrate these equations in an efficient way, and one of them is the leapfrog algorithm. And here you take the half-time step results and get the next time step based on that. So molecular dynamic simulations are based on the idea of ergodicity, and this means that the average in time is very similar to the average in some ensemble. So for instance, if we want to get the statistics of this cup, the thermodynamical properties of this mixture here, we can watch the properties around along the time, but also we can take several measurements, independent measurements, and the average in principle of the independent measurements will approach the the time average of the measurements. So in the case of the proteins, I showed you before that the landscape will look like a mountain landscape, and then you want to move around and surpass the barriers and go through the valleys and the other way around. So in classical molecular mechanics, one deals with several types of ensembles in order to get the thermodynamical properties. So one of them is the microcanonical ensemble. I will see there are some questions in the chat. Let me see. It says that I will take these questions after the talk. And here we have the microcanonical ensemble, where the partition function is computed in this way. So the partition function is the essential function that you need to get all the other thermodynamical properties. For instance, the entropy is given as the logarithm of the partition function. In the case of the canonical ensemble, which is called MVT, the partition function is given by this average over the exponential function. And here, a classical potential thermodynamical function is the free energy, which is given as the logarithm of the partition function. And there are other statistical ensembles like the isothermal isobaric and grand canonical if you want to change the number of particles during the simulation, for instance. So regarding the thermostats, MVE is obtained by solving the Newton's equations. Basically, in MVT, you can use several thermostats like Berendsen, velocity rescaling, and Nose-Hoover, and also Nose-Hoover chains. And Berendsen, for instance, is very good for equilibrating your system, but it's not recommended, and I would say shouldn't be used for data production because it doesn't reproduce the canonical ensemble, right? And there are some papers about that. So if you want to equilibrate the system, then it's fast to do that with Berendsen, but for getting the properties of your system is not recommended. For MPT, you can use also Berendsen and Parinello-Raman. These are available on GROMACS, for instance. So once that we have the potential energy function, we know how to solve the Newton's equation, then we are left with solving most probably millions of Newton's equations at the same time. And this, if we have just a computer with a single core, this will be equivalent to a lane of clients who are trying to pay, and there is only one cashier at a time, right? This is called the serial computation. So currently in HPC systems like Kebnekaise, there are many equivalents to the cashier, which are the cores and can solve the things in parallel mode, and then can make the things faster. But also at the same time, when you increase the number of cores, then you can solve much more larger size problems. So as in this case. So this is a picture of Kebnekaise. And there are several schemes that you can use to speed up your calculations. One of them we have seen yesterday. There is a MPI parallelization, which involves the communication across cores. And also you can use the MPI OpenMP. As this is a technique that is easily to observe in GROMACS, where you combine the number of MPI and OpenMP threads. And besides that, you can use algorithms like domain decomposition or multiple communicators to speed up even further the equations, solving the equations. So this is a typical loop that you have in a ND program, where the number of particles, where a loop for updating the forces or the positions of the atoms goes from 1 to the total number of particles. Then dividing this loop into several cores will in principle speed up your calculation. So other techniques that you can use is a coarse graining. There are already force fields for doing this type of calculations, especially in the protein field. And in this slide, I wanted to show you the time scale for the different types of algorithms and different type of simulations. So here at the bottom we have the ab initio calculations, which allows you to observe time scale in the order of femtoseconds. And because they are quite computational expensive, one can deal with a few hundred of atoms. And currently, one can achieve around 1,000 of atoms, but not more than that. If you want to go beyond that and study more atoms and at the same time larger time scales, then you can use a semi-empirical method, right? And if you want even larger time scales and achieve in the order of conformational changes, then classical molecular dynamics, together with some enhanced sampling algorithm, can help you at this point. So these are the trends that you can see here. And regarding the software for molecular dynamics, there are several packages available: NAMD, GROMACS, AMBER, OpenMN, CHARM, for instance, that can help you. Yes. And they are very well optimized. So in the present course, I decided to use NAMD for several reasons. One of them is that it's available at HPC2N. And another reason is that there are already several courses and material available for GROMACS, but I haven't seen a lot of materials related to NAMD in the other SNIC centers. That's why I thought this was a good idea. And also, why Gaussian? Gaussian is installed at HPC2N as well, and it's compatible with the version of NAMD that is installed. So these are the common steps that you need to follow in order to do a molecular dynamics simulation. First, the initial step is setting up the system. So here involves, for instance, correcting the initial crystal structure if you have that, or if you don't have that, for instance, in the case of the clays, it's more difficult to get a initial crystal structure. They are available, but not for many systems. And in that case, you need to set up that manually and use some geometry knowledge to set the system. Also correct the system if you have the crystal structure, but some atoms are missing, or it's not the structure that you really wanted. So this involves a lot of text editing, right? So once your system is ready, it contains everything that you want. Then you can go to the minimization step where you start using your NAMD software, and uh, then you can also do a solvation and neutralization. And also after this, you can run the minimization step for the whole system, and then do an equilibration step. This is commonly done with the MVT ensemble that I showed you before, and the production is done with the MPT. And once you get your trajectories, you can do the analysis with any tool that you have at hand. And these are some literature that I collected for you, and they are very well comprehensive. So, is there any question from your side? I saw there were 2 questions on the chat.
Yes, I just when you mentioned this ergodicity in terms of molecular dynamics, I think it works well if we have a well equilibrated system, so that statistically it will match. Just because your cup of coffee where milk still didn't dissolve completely in coffee, yeah,
Yes,
brought me to this idea.
yes. Thank you for this great correction. Yes, that's true. That's true. Thank you. It's valid for equilibrium. If you are out of equilibrium, then this doesn't apply. There are other tools that what can you. Hello?
Yes,
Yes, can
we
you?
can hear you again now. We hear you again.
Okay, yes, this is very weird. I don't know what happens with my microphone. Sometimes it decreases the volume, and sometimes it turns off. So please, if you don't hear me, just let me know, and I can correct it. So yes, there was a question related to the link on this slide. What link was that? Sorry. Okay, maybe you can write that question on the Q&A, and then I can take a look at it, because I don't know the slide number you are referring to. So okay, now let me go to the exercise, right? Just to have more time for the exercise. So I will stop sharing at this point. And then I will show you the exercise that we are following today. So if you go to the course website and go to MDQM, you will see here a README file, right? And the first part is what we will do at this point, setting up a AMD simulation with NAMD and VMD. So the instructions are here as a recipe. So please follow that and let me know if you find some problem with that. So as you have seen, we have going through an update of the software at HPC2N. So I tested that a few days ago, but it seems that some tool chains and dependencies can change. So please let me know if you are getting some error at some point, and I can assist you. And the first part, you can see that you need to download a PDB structure from the protein data bank. This setup is very biased towards the protein system because these are the systems that I have dealt with. And now, as I mentioned before, you may need to correct the initial structure and do some setup here using VMD, which is a molecular visualizer for MD trajectories and structures. Then here is an important step. You need to download the chart 36 parameters and do some modifications. And then you set up the system for the protein. This is a adenylase kinase protein. And here you solvate the system as we saw before. Ionize the system to put some sodium chloride ions at a certain concentration. And then you generate the files necessary for NAMD, which are the PDB file, which includes the coordinates, and the PFS file, which is the file which includes the information related to the topology of the molecule and some parameters. Okay, in this part, you will have to correct the topology files that you got from the Makerel website cited above. And this is a common thing that you need to do with all these files starting from the PDB. You need to edit that, especially if there are some atoms in your system that are not included in the topology files and the parameter files, and you may be interested in, as I said before, if you have non-standard residues for proteins, for instance, or some kind of strange atoms in your system from which the parameters are not included. For instance, maybe you want to study some uranium atom, and you may need to parameterize that first and then put these values into the top par files from charm or the other force fields. So the NAMD configuration file is called for AKE, equilibration and configure. And here you need to adjust some parameters. And there is a string called fix me that you need to correct based on the calculations that you did in the previous steps. And now, once you correct this configuration file for NAMD, then you can submit the script with the namd.sh name. And finally, we can do some analysis for this script. So basically how this script look like for the input script of NAMD. You can see that I adapted the job from this tutorial of NAMD to use the 4AKIE protein. This is what you need to correct: the structure, initial structure, and the coordinates. This should be the PDB file, and this the PFS file that you got from the previous steps. This is the initial temperature of the system, and because we are starting from the beginning the simulation, this is the 0 value for the time step. And here we set the type of parameters that we will use. In this case is charm, and the parameters are here. And also I included the parameters for the water and ions here. The temperature is set here with this variable that we declared above here. As you can see, NAMD uses TCL language for setting up values of the parameters. So these are the parameters that we will use for the cutoff: 12 angstrom, the switching on, the distance for switching, the pair list is for the neighboring interactions. The time step will be 2 femtoseconds. Rigid bonds is recommended for this type of simulations. And now this type of multiple time step, where the non-bonding frequency is updated every time step, and the full electrostatic frequency is updated every 2 time steps, right? So the type of temperature control is Langevin, and these are the parameters for Langevin thermostat. Periodic boundary conditions: correct these fixes with the ones that you got from the previous steps. This will tell you that the cell is a cubic box, and these values must be the same in this case. The cell origin is the place where the origin is in your simulation. PME is used for the electrostatics. You say yes, and here you are setting the pressure control and enabling the pressure control and Langevin as well. And this is the frequency for writing the output of the files. Restart frequency every 500 steps. The DCD, this is for the trajectories file, and also this file, which is extended frequency. This includes some values related to the cell evolution. Here we'll print out the energies of the system and the pressure. First, you see here in this script, we will minimize the system for 1000 steps, and then we will turn the temperature and run 2500 steps. Okay, so If you have any question, please just let me know. We will have 30 minutes for this exercise.